Comes the most important equation, which is called as central limit theorem. If your population follows normal distribution, your sample would obviously follow a normal distribution, right? So if your population follows normal distribution, your samples that you're trying to choose would also follow normal distribution. However, if your population does not follow normal distribution, still your sample would follow normal distribution approximately, provided your sample size is large, right? So your sample mean would follow normal distribution provided your sample size is large. Now this question arises on what do you mean by large, right? There has to be a meaning. If you say large, how do I quantify that? And here we go. If you have a sample size of 30, that is considered as large enough. However, this is very subjective in nature. For example, if I'm into outer space mission, manned missions for outer space, that means sending human beings to outer space. How many years would it take for me to get 30 sample size? How many years do I need to wait to ensure that 30 people or 30 different manned missions go to space, outer space? How many years would it take? A lot of years, right? Say 10 years or whatever be. Now, if I'm into manufacturing and say I'm manufacturing shirts, how many shirts do you think get manufactured in a typical company in a day? Anyone? Number of. It can be to the tune of thousands, right? So out of thousands of shirts, choosing only 30 might not make sense. Out of say 50 or so satellites which are being launched to the outer space, picking a sample of 30 is too high. Hence, this simple thumb rule of sample size of 30 is just to get started for y'all, for the initial analysis. So what you ideally do is you select the sample size of 30, and once you get those 30 data points, you again calculate skewness and kurtosis and get a different sample size by substituting in these two formulae. And then you refine what is your sample size. And this is an ongoing process. For example, let me try to explain it using a simple calculation. Say I have this MBA data set. Say I pick 30. Just to explain you, I'm doing this. Say as part of first step, I've collected 30 data points because that is what my rule of thumb says. Choose n greater than 30. But as I've told you, this is very subjective. This n equal to greater than or equal to 30 may or may not hold good. So what do you do? For all of these data points, 30 data points, you try to calculate the skewness and kurtosis, right? And say I've calculated skewness, it came up to be 3. And say I've tried to calculate kurtosis, it came out to be 2. Now what you do is with these 3 and 2, you use this formula, n greater than 10 times of k3 square. So what you do is n, the sample size should be greater than 10 multiplied by 3 square. So 3 square is what? 9. 9 multiplied by 10 is 90. So the next time you pick up a sample, you need to pick up a sample of 90. Assuming that for these data points, its skewness is so much. Are you getting this, or do you have any doubts? Got it, Aparna? Yeah. So in Excel sheet, you need to use the skewness, right? When I've selected all these data points, it turns out to be minus 0.15 exactly, if you want to calculate exactly, rather than doing these approximations. Then what do? N greater than 10 and minus 0.15 whole square, right? So I can do it in this way, is equal to 10 multiplied by minus 0.15 whole square. Uh, what's going on here? I think there is something wrong with the calculation. But in this way, you calculate the sample size. And next time you pick up so much sample size, okay, and then you again, once again, for the sample that you pick up, you calculate the skewness and substitute in this equation. Once again, you collect the sample size, whatever this equation gives. Once again, you calculate the skewness for the sample size. Again, you calculate whether n is greater than 10 times of skewness square, etc., etc. And this process would go on and on and on.